Today, I would like to present our homework 5 assignment project, the diffusion probabilistic models, DDPM, DDIM, latent DDPM with CFG. First, I would like to provide an overview about diffusion models. Diffusion models are a probabilistic framework for data generation. They transform data into noise through a series of incremental steps, the forward process, and learn to reverse this process to generate the new data samples. The key components in diffusion model involves a noise scheduler, a forward diffusion process, and a trained neural network to denoise and reconstruct the data during the reverse process. And these models are widely used in generative tasks such as image synthesis, audio generation, and molecular design, achieving state-of-the-art results in fidelity and diversity of the outputs. For the first part, we did a baseline implementation of the DDPM and DDIM. We used U-Night structure to model the noise added for the diffusion model. We trained using DDPM scheduler and used the DDIM for inference. One challenge was the computational expense and the long training time, with each epoch taking over 1 hour. And for inference, we generated 5,000 images unconditionally. The metrics we used were FID and inception score. The FID score was 261 and the inception score was 4.45. Although these are not the good scores, we did observe some structure in the generated images. We also compared different numbers of inference steps and noticed that while DDIM can reduce inference time, it can also lead to blurriness when reduced too much. Next, we implemented latent DDPM with CFG. We used pre-trained VAE as encoder and decoder. The encoder generates parameters for a Gaussian distribution in a lower dimension, and the decoder converts this to a high resolution images. This approach has the advantage of working on low dimensions while generating high resolution images. We observe faster training and conditional data generation can be easily implemented. However, training still took a long time due to limited resources. We experimented with different hyperparameters, such as U-Night channels and the number of residual blocks, and settled on configuration that offered stable training. For inference, we generated images using different CFG values, showing how CFG impacts the image generation. So CFG 5.0 yielded better inception scores and FID scores, but the images are blurrier than compared to CFG 2.0. In this graph, each row represents a class, and different rows are just different classes. For the advanced technologies, we tried to implementing latent consistent model. This new class of generative model is designed to accelerate the sampling process in diffusion-based generation. The model aims to directly map noise to clean counterparts using a flow-based ODE trajectory. Although this technique promises faster training time, we are still in the early stage of training and do not have complete results yet. Given more time and resource, we hope to further improve our model performance and image quality. In conclusion, our exploration into diffusion models, including DDPM, DDIM, and the latent DDPM with CFG, showcase the potential challenge of these models. With more training and resource, we are optimistic that we can achieve higher quality output and faster training process in the future. Thank you for your attention.